Hello everyone. Myself Divavardhan Singh, and today we are going to start one of the very most important topic. Okay, so first of all, imagine yourself blindfolded on a hilly mountain, and your goal is to find the lowest valley. What you will do? You'll feel the slope under your feet and take a small step downhill, then again and again. Now, that's literally what a AI model does when it learns. This is called as gradient descent. Okay. Now, when we train a machine learning model, we have a loss function. Think of it as a score that tell you that how wrong our model is. Okay, so low score means better model. Our job is to find the setting called the parameters theta that make the score as small as possible. Okay, you have a formula, so take it as an analogy as loss function equal to mountain, parameters equal to GPS coordinates, and finding the valley is training the model. Okay, we can't just escape, we can't just guess the best setting. Real models have million of knobs, so we use a iterative method that it starts somewhere, check which way is downhill and take a step and then repeat it. Okay, moving forward, we have four flavors, a quick table. There are few versions depending on how much your data you look at each step. First is the batch gradient. Look at all the data before each step slowly but accurate. Good for this is good for tiny data set. Second one is the SGD. What it do it? Look at just one example, super fast, very noisy, like a drunk hiking. Okay. Third one is the mini batch SGD. The sweet spot, look at 32 to 512 examples per steps, default for deep learning. This is being used in the deep learning mostly. Fourth one is the one of the most important, and what we are going to use is Adam and the AdamW. Okay, so it's smart mini batches with auto adjusting step sizes. They are being used in the GPT, BERT, and VIT. VIT is Vision Transformer. Okay, moving forward, we have the core idea update that every vision use the same basic formula. Okay, theta new equals to theta old minus n into gradient. So the new position equals to old position minus a step downhill. The gradient is just don't say that which direction is uphill. We subtract it to go the downhill. The neta is the learning rate, that how big each step is. More on that in a second. We're going to see. Okay. Here shows a simple curve with the ball rolling down to the bottom, arrow showing each steps. Yeah. Moving forward, we're going to discuss about the learning rate, the momentum, and the adaptive methods. So the learning rate neta is the single most important hyperparameter. Think of it as a stride length on the mountain. Two small baby steps which you do, you'll reach the valley eventually, but maybe after a week. Neta very large, giant leap, but you overshoot, you bounce back and forth and never settle. Just right, any between value, steady, confident descent, loss drop smoothly. Okay, a smart trick to find the neta is the LR range test. This has been given by Smith. You can have a paper on it, which was written in 2017. You slowly increase the learning rate and watch when the loss function start getting worse. The sweet spot is just before that cliff. Tools like Fast.ai and PyTorch Lightning do this for you. Okay. Secondly, we have the common schedule, step delay, lower LR after every n epochs. Second one is the cosine annealing, that is the smooth reduction, and third method is the linear wrap up, then delay. Okay, it was standardly used for the vision transformers or the transformers which are used in GPT. Yep. Moving forward, we have momentum. Okay, so what momentum showcases that you should stop the zigzagging path. Okay, plain gradient descent zigzags a lot. A momentum fix this by giving a ball memory, like a bowling ball rolling down. It build up speed in the right direction. The formula for this is given here. Velocity carry forwarded. Typically, the value for the beta is 0.9. We take. Okay, so the analogy for this is that a bowling ball versus a marble. A bowling ball doesn't stop at every tiny bump, it rolls through it. So that's the momentum. Yep. Moving forward, we have the Nesterov accelerated gradient (NAG). It's a very smart version. It's like a peek ahead that you get the information about it before. It gives you a time complexity of big O of 1 by t square. And it converts. It's roughly as fast as twice of the mathematically, as we can see. Moving forward, we have the adaptive method. Okay, what if each parameter could have its own learning rate? Okay, so that's the idea behind the adaptive method. We have four of them. AdaGrad is the adaptive gradient descent. Divide neta by the total number of pass gradient. This is good for the sparse feature, but neta shrinks to zero over time as it forget how to learn. Second is the RMSProp. Same idea, but you uses a running average instead of a total sum. So old gradient fades fixed by AdaGrad dying learning rate. Okay. Third one is the Adam. This combines momentum plus RMS prop and bias correction in early steps. So the beta 1 can be 0.9, beta 2 can be 0.999, best general default. Moving forward towards the 4 point, that is the AdamW. It's Adam plus proper weight decay separation, standard for the all transformers like the BERT, GPT, and VIT. Okay. Now Adam's default are neta equals to 0.001, beta 1 equals to 0.9, beta 2 equals to 0.0999, and eta equals to 1 into 10 raised to the power minus 8. So you really need to change them. Okay, they are some of like a default or a go-to optimizer. Yep. Moving forward towards the practical tips and the pitfalls and the key takeaway. Okay. So when we even the experienced ML engineer falls into these traps. So let me tell you this all in a plane. First one is the unnormalized input. If your feature are on widely different scale, for example, age gap 0 to 100 and salary 0 to 100,000, the loss landscape become a very narrow ravine and a gradient descent struggles. Okay, so for that you have to use a pre-processing process where you'll do the batch normalization for it. Second point is the constant LR with Adam. Okay, don't just set a learning rate and forget it. Use a linear wrapper for first 4 to 10% of the steps and then a cosine align, which we have already talked before. Okay, this is used for critically for the transformers. Third one is the gradient exploration. Sometime gradient grow or astronomically and your model breaks the NAN loss. Okay, this is also can be fixed by the gradient clipping. If your gradient size is greater than C, that is usually a constant, scale it down. Okay, moving forward, we have batch size. When the batch size is too large, big batch sizes are tempting, but the gradient noise of a small batch size is actually a feature. It helps the model to escape the sharp minima that doesn't generalize well. Yes. So moving forward, we have the quick references given here. You can see it here. But before that, we'll move to some of the key takeaways. Gradient descent equals to the blind hold hiking, which we have already seen via example. Second thing, that the SGD plus momentum often generalizes better. Adam and AdamW, when you'll start code, you'll use Adam and AdamW as like daily part of a code. Okay. Third one is that the learning rate is the most critical hyperparameter. So optimization for this is very important. Fourth is the adaptive method estimation per parameter curvature can be used as your first and the second momentum estimation. Okay, this is the very important point. Fifth one is that always normalize your input. Okay, clip your gradient and watch both the training and the validation loss. When you are working over the gradient descent, this training and the validation loss curves are need to be taken into account. So that's all about the gradient descent. Okay, we have covered what is AdamW and about that. So drop a comment if you want to know anything more about it. Thank you.